This article is improvement of CluStream algorithm using a sliding window for the clustering of data streams. Authors are Sahar, Ahsani, Dr. Morteza, Yousef, Sanati, and Dr. Muharram, mansoorizadeh. Data stream. Today, data are generated in large amounts, mostly in form of data streams. A data stream is an unlimited stream of data that is generated in large volume and with high speed. Therefore, it can be defined as a sequence of data objects in a specific time intervals. Data stream clustering. One of the most common processes performed on data stream is clustering, which is aimed at dividing the data items into homogeneous groups. Data in a single group have the highest similarity, while the data greatest difference with data from other groups. Window models. As the length of the stream has no limit and storing the data is not possible, a stream processing algorithm which view the input sequence as a window and process the part of the data which is visible through the window. There are several types of time windows in the study of evolving stream. The most common windows include landmark, fading, tilt, and sliding windows. In the landmark window, a specific time point is used as a start time, and so far all data samples are considered. In this window, the data doesn't lose its value over time, and all the data in the window is equally important. This window is not suitable for applications where recent information is more important than past information. And fading window. In this model, each data sample has a weight that depends on the arrival time. A new data sample takes the highest weight. This weight is gradually reduced by the decay function. This model doesn't completely discard the data sample, and all data is active and has a weight that depends on their age. In fading window, newer data samples are more important. And tilt window. In this model, data at different levels of granulation are stored from the structure. As a result, the latest data is stored at the smallest grain size level, while the old data samples are stored at the larger grain size level. This window model focuses more on recent data, such as the fading model, without removing all data completely. Sliding window. It's a fixed or variable size window that slides on data stream according to time or number of data samples. In fact, the latest data samples are always considered, and when new data samples are received, all data that is not located along the window is removed. Proposed algorithm. As you know, one of the existing algorithms for clustering is CluStream Algorithm, which is implemented in the Apache Spark distributed environment. In general, this algorithm is a two-phase algorithm that uses a tilt time window. This window doesn't completely remove the old data sample. The present paper offers a modified version of the algorithm which utilizes a sliding window for clustering. In the proposed method called CluStream Assembly, only the latest data are used in updating the produced model, and the old data are removed. In other words, in this model, by sliding a window on the data, expired data that is not located along the window is completely removed. Therefore, only recent data is visible. This makes clustering in limited memory and more quickly and achieves more desirable result. The CluStream SW was implemented in Apache Spark, and the modifications are only confined to the online phase of the original algorithm. CluStream Algorithm. As I mentioned, CluStream is a joint two-phase framework for the clustering of data streams. The two phases include online generation of statistical summary and offline phase use of the summarize. This online phase analyzes the data stream and storing statistical summaries. Summarization in the online phase results in clusters, which are called microclusters. When needed, the offline phase makes use of the summarize to provide the user with the final clusters in different time horizons. The data structure used for storing microcluster is called cluster future vector. These vectors are constantly updated as new data enter. In CluStream, CF vector is a tuple in form of CF2x, CF1x, CF2t, CF1T and N. N denote the number of data samples in the cluster. CF1X a linear sum of n data samples, and CF2X is the square sum of n data samples. CF1T and CF2T denote the sum and sum of the squares of timestamps from n data samples in each microcluster. In the online phase of CluStream algorithm, which is the initial phase of the algorithm, the initial microclusters created using the k-means algorithm. Next, the process of updating the created microcluster begins. Whenever a new data sample enters, either the data sample will be observed into one of the existing microclusters based on proximity, or the data sample needs a new microcluster, but given the limitation of the fixed number of microclusters in this algorithm, the number of clusters must be reduced by 1. This can be done either by removing one of the older microclusters or merging two closed microclusters to each other. In general, CluStream uses the tilt window model. This method summarizes recent data with higher precision due to the pyramidal pattern. Nevertheless, CluStream cannot record the precise scattering of recent data. The reason is that as the data stream enters incessantly, the radius of a cluster gradually increases because the expired data are not completely removed from the window. So more data are added to each cluster over time, which ultimately reduce the precision of cluster. CluStream SW. In the proposed version, we have made changes to the process of dealing with data samples. The changes include the structure of microclustering, online phase of the algorithm, and updating microcluster using sliding window. In our method, the microcluster structure of CluStream has been improved. A microcluster contains a set of d-dimensional data samples that represent as a tuple of CF2X, CF1X, N, and TL. As in the basic algorithm, N, CF1X, and CF2X are the three components of CF vector, as the same as the CluStream algorithm. And the new parameter TL has been added to the CF vector, which denotes the time of the last update of the microcluster. Actually, we have removed two parameters of CF1T and CF2T and add TL parameter instead. And the online phase of the algorithm has changed slightly. When the data sample is not observed by any of the existing clusters, a new microcluster should be created. As the number of microclusters is fixed, in such a case, CluStream algorithm either removes an old microcluster or merge to closed microcluster so that a new microcluster could be created. Thus, creating a new microcluster depends on the removal of an existing one. In the proposed algorithm, some modifications have been made in the way the algorithm deals with data samples. In this method, the number of microclusters is determined dynamically. New microclusters are produced gradually and only if they are needed. When the number reaches the maximum threshold, the behavior of proposed algorithm resembles that of CluStream. And when the distribution of the data stream changes and new clusters are created, in other words, after processing of clustering, those microclusters which lie within each other's overlap radius and which are likely to belong to the same microcluster will be merged. Updating microcluster using sliding window. As I mentioned, in CluStream, as the enter constantly, as the data enter constantly, microclusters are stored at different levels of granulation. Nevertheless, CluStream keeps the old data samples in the stream history and may never remove the absolute microcluster. But CluStream SW uses sliding window for a more optimal clustering. The sliding window is determined by its range and step. The range of sliding window R is determined to keep recent data as Step S determines a section of range that moves out of the window when the window is moving forward. As mentioned, the sliding window technique only uses the most recent data to update the model. Therefore, CluStream Algorithm can create more precise clusters by focusing on the recent data streams that lie within the length of the window. This figure shows how to remove data samples from a microcluster. As shown in the figure, if we assume the number of samples of data entered per second n equal 4, range of window r equal 3, and movement step s equal 1, as I mentioned, samples that lie outside the window will be removed. As the data stream enters every second, the microclusters are updated. Next, when a window moves one step forward, T4, the data sample of T1, which are now expired, are removed from the window so that the current window could only observe the recent data. Algorithm evaluation. To evaluate the performance of proposed algorithm, we have evaluated the speed and purity of algorithm. The purity is an external evaluation. To compute the purity index, we consider the average percentage of the dominant class in each cluster. For evaluation of precision, the algorithms were executed 4 times at the average values of the purity index were recorded. We use 2 real-world datasets called cover type and power supply. Cover type dataset is about the vegetation of the United States forest, and power supply dataset is about the hourly power supply of the Italian electricity supplier. Result figure 2 and figure 3 compare the quality of clustering in Spark CluStream and CluStream SW with range of the window 4 and the number of data is 1000 per second. As can be seen in the figures, in most cases the precision of clustering in the proposed algorithm is more than Spark CluStream on different datasets. And figure 2 and figure 5. Figure 4 and figure 5 show a comparison of the clustering quality in Spark CluStream and CluStream SW with range of Windows 6, and a number of data is 2000 per second. As can be seen, the proposed algorithm produced a better result in most cases. In figure 5, when the first window is formed, the quality of both algorithms is also similar, but they gradually begins to differ. Although the precision of clustering on power supply dataset is generally low, but the proposed algorithm show a relatively higher precision. And in general, our algorithm performs up to 13% in the cover type dataset and up to 17% in the power supply dataset, better on average in terms of precision, and in some cases more than 90% improvement in precision in achieved. Figure 6 and figure 7 show the execution time of the CluStream SW and Spark CluStream on 2 different datasets. As the time length of processing, the data on cover type changes over time. The proposed algorithm at its best performs 50% better than the basic algorithm. On this dataset, the processing time in power supply was in some cases longer than the main algorithm. This is because removing the data samples in the online phase is time consuming. In general, the proposed algorithm may sometimes have a longer execution time because of removing the data samples every second, but its performance will gradually improve as the data stream is constantly entering and the number of microclusters is not fixed. As a result, the proposed algorithm is more efficient on larger datasets. And conclusion, in this paper, we discuss an efficient data stream algorithm called CluStream SW for the clustering of large data streams. CluStream SW produces cluster from sliding window and removes expired data by sliding the window. Therefore, the latest data are always processed in each window, which makes clustering more efficient. And the PROS algorithm performs better than Spark clustering in terms of the quality of clustering and in some cases in terms of speed. As a future work, we provide a solution for handling outlier data and mechanisms for reducing the effect of noise is needed, and adding the ability to work with the variable length of the sliding window can be another future work.